Hi guys, I'm back with another topic here. So in this part, we will be discussing uh, the results of the models that we get. So in total, I have trained 5 models, in which one of them is a dummy classifier, also known as a random model. So in this random classifier, there is no rule that it follows. It randomly assigns the prediction that it sees as rational. So in this function, I have these many inputs: x train, y train, x valid, y valid, x test, y test, and this another argument. So this is nothing but the model path uh, where I want to save the model after training, the model name, and some validation to avoid retraining. So we also saw the same structure in the previous videos where we save the data to avoid the continuous repetition, right? The best part of scikit-learn is we just need to change the class name for whatever model we train, and the rest of the methods are very same. Since we are dealing with predictions, that to the probabilities, and also we also have multi-log loss as metric, right? So, so here the probabilities are very important. So in that case, we calibrate the probabilities, and that is very important. And let me tell you how calibration is done, how calibration is useful. So when the probability estimate of a data point belonging to the class is very important, and moreover this is highly balanced, and we want to make sure that the probability of the estimate belonging to the class like is the highest priority here. So we calibrate the probabilities, and scikit-learn has amazing functionality to calibrate the data easily. And by default, we use sigmoid method. It's one of the techniques to get the probability value. So sigmoid graph is something, sigmoid function is something that returns only the value between 0 and 1. And we can take it as a probability value, right? And this is initially when we are running this, it trains the model. And the next time when we run, since the model is already saved, we directly uh, go to the else part without retraining it. That's the specialty of this code. And I'm saving the model with the help of pickle. Simple concept. We also saw this in the previous videos. Now, once the model is trained, we predict the probabilities. So there's a function called predict proba to get the probability values. So I have already trained the model. So I can get the probabilities for training, testing, and validation, all these 3 sets with the same object. So white train preds the probability values and the log loss, multi-log loss for the same. And I'm just printing it. Same concept I'm repeating for the validation part and the test part. And once I get all these values, I can show the plot. If show plot, if this is nothing but the confusion matrix, recall matrix, and precision matrix that we want to show for every model. Whenever it is true, it displays the plot for us. So simple concept here. I'm getting the actual predictions and plotting the confusion matrix. Apart from that, I'm also returning the report, classification report. So from the metrics class, so we have something called classification report. We just need to pass our original targets and predictions, and it will return the report, the entire report of the model performance. And finally, we return the train log loss, valid log loss, and the test log loss. in this uh, in this function at the end totally. Now we can call the function for the dummy classifier, and it returns these results, like the training log loss is 2.680. The agenda here is to minimize the log loss to make sure that it is near to zero. But due to some reasons and class imbalance, and moreover, this is a random model, we get to see 2.6, which is highest, which is higher value. Similarly for validation and the test, it is quite similar, but you get the point, right? The confusion matrix here, since it's a multi-class task, we get to see this big confusion matrix, and this is the precision of the confusion matrix. So we get to see that the model only predicted to be latency depth for every point, and this is mainly done. This is because it's a random model, and latency depth has the highest count in the whole data set. And this is a recall matrix. We get to see in precision, we get to see the quality of the model trying to predict the positive point. In recall, we get to see the how well the model retrieved from the whole positive set, how well the model actually able to predict the positive point. That's how we discussed in the last part. And this is a recall matrix. We can say that when the model is performing well, we get to see the precision and recall matrix, the diagonal part, to be highest. But we don't see it here, and for obvious reasons, it's a random model. And this is the classification report. If we clearly observe, latency theft has the highest recall, because that's what the model predicted to be the point, class label, predicted the class label as. And we get to see other metrics also. This is how it is done for dummy classifier. Same thing, we are doing it for logistic regression. Locally, I have done the hyperparameter tuning, and it happens to be the best values for logistic regression are penalty regularizer to be L2, and C, it's one of the parameters, and it is the best value is 30. And njobs is for parallel processing. We take it. So same model path and model name, I'm giving it for how I gave it for dummy classifier. I'm giving it the same for logistic regression. Same parameters, training and dumping the model and reading the model out of it, object, doing the predictions, plotting the confusion matrix, and returning the losses. When we observe the results, the training loss is slightly lesser compared to the dummy classifier. The reason behind creating this dummy classifier is to see whether the actual models do well apart from predicting the highest class level. And since the loss is reduced, we can say that the model, logistic regression model, is doing well compared to dummy classifier. This is the confusion matrix, recall precision matrix, and in this we can see some of the points are highlighted. Diagonally, if you also observe, there is a pattern going, but the the crime classes which came really less often are not well predicted by the model. And the recall, we can see there's a slight pattern of diagonal, but it's not perfect. Similarly, in the decision tree classifier, I have done the hyperparameter tuning, and these are the best values that I have obtained. Model name, model path, saving the model, loading the model, and doing the predictions, getting the loss is same. The steps are same. Showing the plot and returning the losses. The steps are completely same. But one thing to observe here is the loss is very less compared to logistic regression. It's 2.34, whereas logistic regression was a 2.5. So we can see a slight reduction. And this is the confusion matrix. The precision matrix, we can see the diagonal to have a slightly diagonal elements to be darker, but still it did a pretty good job. See, coming to recall, the same structure. So this precision and recall, if you observe the values, latency, theft, burglary, assault, these are the points which the model tried to predict accurately. Now comes the random forest model. This is one of the ensemble models, which in return uses a lot of decision trees in the background to predict the point. So again, same concept, same structure I'm following. Random forest model classifier. The best values for it are these. Calibration, saving the model, loading the model here, and then doing the predictions, finding the loss. Same structure. The loss is slightly higher than the decision tree. It can be because of uh, various reasons, because random forest uses ensemble techniques, right? So it consumes so many trees to predict a point, and there are chances of overfitting as well. There can be issues, but yeah, it's the same recall, precision, confusion matrix, and the classification report. And now comes the XGBoost classifier. This is one of the ensemble techniques which follows the method of boosting. This is slightly advanced model, and compared to previous models, XGBoost is really, has done a good job in reducing the loss, and the loss is very less, to 2.0. It's equivalent to 2 something. And the confusion matrix, precision matrix, we can see the proper pattern of diagonal elements to be darker, and this is one of the signs that the model is doing well. And the recall, we can still see a pattern there. Arson, assault, bad checks, driving under the influence, and these are the points which the model exactly predicted, that's how the precision ratio is. And here the latency theft, the recall is higher, and it's one of the positive indications. We have other points which are of same kind. And finally, we have the summary. So this summary tells you everything, which model performs well and which models does not perform well. Clearly, it's XGBoost because the loss is very less, and this can be used for production. But still, we can try other boosting techniques like cat boost and light GBM. This is something to be experimented. So the best model as of now is XGBoost. So in the next video, we will discuss how we can predict for a single point and deployment part as well. That's it for this video. I hope you liked it.